hand as well, but it's best if you have questions to ask after looking at it. And next Thursday, no real class, but I'll just be in the Zoom meeting for optional drop-in office hours if you want to drop in and ask some last-minute questions about the final. And that part 2 will be due at 11:59 that day. So that is the plan. So today is our final part 1 review day, and I can't fit everything onto one screen. Final part 1 has stuff from all term. It's all the calculus skill kind of stuff. So chapter 2, we have finding limits from a graph, and we have finding limits from a rational function by hand. We have chapter 3, there are going to be 5 derivative problems using a combination of all of the derivative rules that we know. In chapter 5, we have 2 integral problems. One is finding an indefinite integral using substitution, and one is finding a definite integral by hand. And then chapter 7, there are 2 questions, first and second order partial derivatives. So the practice test has been up for a while to give you an idea of what will be on the final. So I have prepared examples of all of these things for that similar to what to expect on the test and some things, but I want to start by asking if there's anything specific that anyone wants to start with. If not, I'll just pick. All right.
Could we review how to find limits of rational functions by hand?
Yes, we can. I feel like chapter 2 is, well, it is the longest to go, and we don't use it as much. Derivatives we actually use throughout the term, but limits we don't see that often, so yes. Okay. So here is an example to start with. Where's my orders? So the exam itself says specifically on this problem, do these by hand, not by graphing. So this is a rational function because we have a numerator and a denominator. And so our first one is finding the limit as x goes to 1. So what should we do first? There's a couple of things that we might want to do first.
Plug in.
We can plug it in, yes. So in general, when we're doing a limit, we should try plugging it in first. Oops. And see if it works. If it doesn't work, then we'll have to try something else, but we can try plugging it in to see what happens. So when we plug in 1, we get -2 on top. And 6 on the bottom.
-1/3.
Exactly. So in this case, by plugging the number in, nothing crazy happened. We did not end up with a 0 in the denominator at all, no indeterminate forms or anything. So this is all we have to do. So that's a nice, a nice limit situation where we can just plug it in and nothing weird happens. So let's look at part B.
Zero on the numerator.
Is 0 in the numerator. So if we try plugging it in just for fun to see what happens. If we try plugging it in, we'll get 3e minus 3 over 3 squared minus 7 times 3 plus 12. So that is definitely 0 in the numerator. In the bottom, we get 9 minus 21 plus 12, which is also 0. This doesn't work. So this, we actually, throughout the term, did 2 ways of dealing with this. One is an algebraic way and one is a calculus way.
Is this the Hopkins or something?
L'Hopital?
L'Hopital? Yeah.
Yes, that will work. So this is, since it's a 0 over 0, this is an indeterminate form. So one method to do this would be L'Hopital. Because it's an indeterminate form, 0 over 0 is indeterminate. So we use L'Hopital for 0 over 0 and infinity over infinity. So our limit so if we want to use L'Hopital in this case, what would we do?
Derivative
Derivative of what?
of the equation, I think.
Not quite. We wouldn't want to do the derivative of the whole thing together.
Is it just of the bottom?
Partly. So we would do the derivative of the bottom, which would be 2x minus 7. And what happens to the top? Derivative of the top, exactly. So we would do the derivative of the top and bottom separately, which is not the same thing as doing the derivative of the function, because that would require a chain rule. So it's just derivative of the top and of the bottom for L'Hopital. And then this is no longer indeterminate since there's a 1 on top. So that's definitely not going to be indeterminate. And we end up with 1 over.
-1.
Yeah, so we can just plug it right in that case. So that's one method that you can use. And remember, L'Hopital means doing the derivative of the top and the bottom separately as separate pieces. What is the other thing we could have done here to find that? Let me move this out of the way.
Quadratic formula? No. Oh, you can put the denominator to the top.
You factor the denominator.
Factor the denominator, exactly.
Oh, that's right.
And really we would factor both the top and bottom, but the top is already done. So by factoring the denominator, we see that we have a common factor on the top and bottom, that x minus 3.
So is that a whole?
Yes, exactly. That would mean that since x minus 3 canceled from the top and bottom, that does mean that there's a whole at 3. So that would be the other method. This still isn't quite done, but the other method would be to factor or cancel common factors.
And you just plug and play.
Yes. Once we do that, we have something that is not going to be indeterminate when we start to plug in. So now we can take the limit as x goes to 3 of 1 over 3 minus 4. Oops, 1 over x minus 4. I merged 2 steps there. So we do the limit of the reduced version of the rational function, and then we can just plug in 3. And we would get negative 1 again. So either of those methods will work. We got the same thing either way. So it really doesn't matter which one you do. I don't care. As long as you do one of these correctly, that's fine. So the method 2 that was listed here, 1 and 2 don't matter. They could have been switched. That's the method we were using in chapter 2 since we hadn't done L'Hopital's rule yet. And that's the method that comes from college algebra or pre-calculus where you're looking for holes in a graph. So we can factor top and bottom and cancel, and our reduced version lets us take the limit. So either one of those.
And then kind of just a simple question. If it were to be a negative sign instead of a 3, would we still use this, or an infinity sign instead of the 3, would we still use the same methods?
No, and that's actually part C, so that's a great segue. So that's our last bit of this problem. So when we have infinity, there's a couple ways to do it, to think about it. But our key is how we, the same way that we look for asymptotes, horizontal asymptotes in college algebra. And we can actually use either the original function or the reduced version. It actually does not matter. So if you already reduced it in part 2, you can use that in part C, but I'm going to use the original just so we have it. So we have x minus 3 So here, x is going out to infinity. It's going out to positive infinity in this case. But even if it were going to negative infinity, we would look at this as we do with horizontal asymptotes. So does anyone remember how we can look at this function and decide what's happening when x goes to infinity?
Set the bottom equal to 0?
No, that would give us the domain. It would tell us where this function is not defined.
It has to do with the degree of the first term, but I can't remember. I don't remember limits, if we're being honest.
Yeah, that's okay. That's exactly right. It has to do with the degree of the top and the bottom. So we have 3 possible cases. And this one, I'm just going to call it case 1. The degree on the bottom is bigger than the degree on the top.
So they're not both 1? Oh, the degree. I was thinking of the coefficient.
Yes, so the leading coefficient of each of these is 1 because there's a 1 in front of the x and in front of the x squared, but the degree is the highest power of the x. So here the degree on the bottom is bigger, which means we don't have to do any more thinking. It's automatically 0.
And if it was on the top?
So if it were, so let's look at these 3 cases so we can talk about what's really going on here. So I'm actually going to first do if they were equal. So if the degree on the bottom is equal to the degree on the top, then the limit as x goes to infinity is the ratio of the leading coefficients. Which means the leading coefficient of the top over the leading coefficient of the bottom. So that's where, if this were an x squared on top, then we would have the same degree on the top and bottom, and we would just take those coefficients from in front of each of the highest power of x's. And that last case is where the top is bigger. And in that case, it's either infinity or negative infinity, and we would have to figure that out. That's the kind of problem that I was letting you graph for your homework and tests when we were doing this, which is a little hint that that's not going to come up on this test since you have to do these by hand. But that is the situation if we're talking about asymptotes. That would be a slant asymptote. So the asymptote would either be a line with a positive slope or a negative slope, which is why our function would be going off to infinity or down to negative infinity. So that is a thing that happens, but
Next to the one that you have degree bottom equal degree top, can you just put like an x squared over an x squared next to it?
yes.
Thank you. Perfect.
So in a from a conceptual standpoint, we kind of talked about this when we were doing L'Hopital's rule in chapter 4 also. If we think about this function, x minus 3 over x squared minus 7x plus 12, this x on top is going towards infinity, and the bottom is also going towards infinity. But the bottom has a higher degree, which means it's growing faster. It's a little bit easier to see, I think, if we look at it in the reduced version. If we look at 1 over x minus 4, that 1 is staying exactly where it is, and the x minus 4 is growing up to infinity since the x is growing up to infinity. So if we have a fraction and the bottom is just huge and the top is just 1 the whole time, that is going to get smaller and smaller and smaller forever, and it will end up being 0. It only changes in the case of in the third case, because that's the only time when there is like a direction happening with the asymptote. But as long as it's case 1 and 2, it doesn't matter whether it's positive or negative infinity. One other thing about these, I don't want to overcomplicate this, but I just want to give you options. This is how we did it in chapter 2, and this is great. You can use this rule of the 3 cases by comparing the degree of the numerator and denominator. We could also use L'Hopital's rule for this one as well, because this is an infinity over infinity situation. Since this is what we're looking at, oops, that's a minus. If x goes to infinity, this top is going to be infinity and this bottom is going to be infinity since they both have x's in them. So we could L'Hopital this just like in the previous one, and it'll end up being the same. So we'd end up with 1 over 2x minus 7. And for the same reasons as I mentioned up here with our reduced version, since the top is staying 1 and the bottom is going to explode and go toward infinity, that whole thing turns into 0. And so L'Hopital's rule would work in this situation whether for any of the cases, not just for case 1. So if you really like L'Hopital and you don't want to remember all those cases, that's a way you can do that. Any other questions about limits of irrational functions? Okay. So on our list of topics, we have done that one. Any other requests?
Chain rule.
Before we jump to the chain rule, could we just go over real quickly on how to do the limits from a graph? I just need a quick refresher.
Yes, I think that's a good idea. While we're on limits, let's do that, and then we can go to chain rule / derivatives in general.
Because like I need some work on the chain rule too, so I'm all about it.
Sounds good. Okay, so here is a graph with 6 limits that we're going to find. So we have, just right off the bat, we can notice that these first 3, A, B, and C, are all going toward -2 in some way. So remembering that on the graph, it's always X going towards that number, so we would be focusing on this -2 right here. And the other 3 are all going toward 3 in some way. And so that would be here. So really nothing else on the graph matters other than what's going on around those 2 values, for this problem at least. So for the -2 here, this first one has this little plus sign up hanging out next to the -2. So what does that mean?
Coming from the right.
Exactly. So we're finding the limit from the right. So we would be coming at -2 from the right, but of course we need to be on the graph. So what would be the limit going toward -2 from the right for this function?
-2, 3.
So the -2 is the X value, but the limit is just going to be the Y.
Oh, 3.
Yes, exactly, just 3. So on the graph coming from the right toward -2, the graph is right at 3 there. So how about if we come toward -2 from the left, like in B?
1.
1, exactly. So here, this little negative up here means from the left. So we would be just hanging out on the graph, writing the graph down toward -2 on the X value, and the Y is going toward 1. So remember, it does not matter that it doesn't actually reach 1 there. The whole doesn't matter, it just matters that we're getting close to 1 when X is getting close to -2. So part C does not have a little plus or a little minus, it just is the limit as X goes to -2.
3.
It does not exist.
Does not exist, exactly. So the value of the function, if we were just looking at f of -2, it would be 3 because that's where the hole is filled in. But if we're talking about limits, they have to be coming to the same place from either side in order for the limit to exist. So if the left and right limit are not going to the same place, then there's no limit there. It does not exist. Let me just write D and E.
But if they asked us, I've always gotten confused of that. If it's asking us what the value is at 3, then it would be through, or at -2, would it be 3?
Yes, exactly. So if we had a, if we had a G here, and if it were just f of -2, so there's no limit here at all, we're just looking for the function value when X is -2, then it would be 3 because there's a little, the graph is reaching 3 when X is -2 there. So function value and limit can match, but they don't necessarily. We definitely can't count on it. So the other three are looking at what's happening when we go toward 3. So what is our limit as we approach 3 from the right?
-1.
-1, exactly. So if we're writing our function toward 3, that function is going toward -1 there.
So all 3 of them would be -1 then.
Yes, exactly.
They all go, okay.
So when we look at the limit from the left, the function is also going toward -1 here. And so this is another place where we really have to think about the difference between a limit and the function value. In this case, the right and left limit are going to that same place, the -1, which means the limit overall is also -1. Does not matter that there's a hole there with a little point above. Since the right and left limits are going to the same place, the limit in general is that same value. And we could say the same thing here. Same kind of thing. If we were to just look for f of 3, the function is not at -1 down there, it's up at 2. So the actual value of the function is totally different from what the limit is. And that's okay. So you're not going to be asked for function values on the test, but that's just a thing to keep in mind. Any other questions or clarifications about these limits on graphs? And just a note, I didn't write it here, but on the test it says no need to show work. So since this one is just, you just have to look at the graph and find the number, you don't have anything to show on these. Okay, so let's talk about derivatives. And before jumping straight into the chain rule, I have can I fit? Yes. So I have 5 functions here that are similar kinds of things to what you will need to do, take the derivative of on the test. So before we actually do any of these, so I want to go over at least some of these. We could do all of them if we want to. But before we actually go over any of them, I want you to just think about, based on looking at the function, which rules do we need? And with a special attention to product rule, quotient rule, and chain rule, because those are the ones that I think get kind of mixed up a little bit, that are hard to identify which ones. Natural log and natural exponential are a little bit easier to spot. But so try to think about what rules are needed for each of these, and there could be more than one rule per function. Also,
Chain rule on 1.
yeah, so take time on your own to think about it
Okay.
first before we do it together. And also, just a little note, I didn't bother putting the power rule in here because it's required for every single one of these. So you can write power rule if you want to. So I'm going to give you a little bit of time to think about that on your own, and then I'm going to take some polls just to see where we're at, and then we can go over some of these together. Okay, so even if you are not finished or unsure, that's okay. I am going to launch a couple polls. So the first poll I'm going to launch is for you to choose which of these 5 require the product rule. And you can choose more than one, but you don't have to. So about 15 more seconds. Okay, I am ending the poll. Okay, so most people did choose number 4, which is correct, but there's a lot of choices for others. So let's talk about this. So the product rule is specifically when we are multiplying 2 functions together. So it's not just when we have like 5 times something. It has to be 2 functions with x's in them. So on number 4 here, number 4 is definitely going to use the product rule. Because we have these 2 separate parts that are being multiplied. So we have the x cubed part, which would be our f for our first in the product rule. And then we have our e to the x part, which would be our s in the product rule. So each of those things, we have x cubed and e to the x, and those 2 are being multiplied together. None of these other functions have that situation. So none of these other ones have one part multiplied to another part to make the overall function. Okay, so I'm going to put up a poll for the quotient rule next. Same kind of thing. About 10 more seconds. Okay, I am closing this poll. Okay, so number 2 was the most chosen, which is great because that is definitely the quotient rule. Quotient rule. And it's the same principle as the product rule where we need to have some sort of function happening on the top and the bottom. So here we have this whole 5x squared on top and this whole 3e to the x minus 2x on the bottom. So those two separately are their own functions in themselves with x's in them. And so this would be a quotient rule situation where we have our top and our bottom. Number 5 was also chosen a handful of times, and the reason number 5 is not a quotient rule is that on this one, I'm assuming it was this one that made people feel like that might be a quotient rule. And it's not because that 4 on top is just a 4 and nothing else. Technically, the quotient rule could be used on that, but it's way, way more work than is necessary. So since it's just a 4 without any x or anything else with it, that would not be a quotient rule. And just before we do one more poll with the chain rule, I am just going to bring up the practice final for a second. You will be given the product rule and the quotient rule on the test. So as long as you know what ones need the product rule and quotient rule, then you can use these, which are given to you. Those are the only 2 rules that are given. Yay, I'm glad that people are happy about that. So product rule and quotient rule, if you're using them a lot, you tend to memorize them, but it's not super necessary. And on a test, our brains sometimes forget things. So those are available. What won't be available or given to you are the other rules. So I already filled in the natural exponential down here for number 4 because that was an e to an x. So anytime you have e to something, that's a natural exponential. This one also used that natural exponential. Which just means that derivative of e to the x is itself. So one more poll for this, and that is which of these require the chain rule? Okay, about 10 more seconds. All right, ending the poll. Okay, so 1 and 3 were chosen a lot, which is great because those 2 are chain rule problems. The rest are not though. So all of these actually got at least a few votes. So let's talk about why some are chain rule and some are not. so here we have chain rule. Oops. Okay, so on this first one, this natural log is our exterior function. If we start from the outside and just look at, sorry, we look at this function from the outside, the first thing that we would see is the ln of x. So that would be our exterior function. Inside of that natural log is another function in itself for x to the 8 plus 3. So that would be our interior. So we have a little nesting of functions here. We have an exterior and an interior. So that would definitely need the chain rule. Number 3, I think this one is a little bit harder to see sometimes that this is an exterior and interior. But just the e in general, e to a power, that's going to be the exterior because there is an interior function in the exponent. So e is not a chain rule by default. I think sometimes people see e and think it's automatically going to be a chain rule problem, but it's only a chain rule if there's another function happening up there in the exponent. So these other e's, for example, this e in number 2, that's just e to the x. There's nothing else going on in that exponent, so we would not need a chain rule there. Same for the e down here and here. None of those are chain rules because they only have an x in their exponent. This bottom one actually didn't need anything special. So actually I should have written, so up here, number 1, we need the chain rule. We also need a natural log rule. Since there's a natural log, that's the hint. Down here, chain rule and natural exponential. Number 5 was not in any of these polls. It wasn't a product rule, quotient rule, or chain rule. This does have a natural log, exponential, and this wasn't in our list, but it does have a beefy power rule at the end there. So you're not going to be told what rules go with what derivatives on the test. So being able to identify what rules you need will be important. So let's actually do at least the chain rule problems. I'm happy to do all of them, but let's start with the chain rule since those are the ones that were specifically requested. I'm just going to copy. Let's start with this one. Okay, so here is number 1. There it is. Okay. Okay, so here is number 1. So we just talked about this one a little bit. So if we are using our chain rule notation, we're going to have an exterior function and an interior function. So the
1 over
interior,
x.
sorry, go ahead.
1 over x for the exterior.
So that'll be the derivative, but what is just
Oh.
the exterior?
Oh, natural log x.
Yes, exactly. Natural log, and I'm going to use the notation that we used in chapter 3 when we did this. So our interior is the I of x, so our exterior function is the natural log of that interior, which would mean the interior is that 4x to the 8th plus 6. So we need to know what our exterior and interior are, and we also need the derivative of each of those. So natural log is 1 over whatever is in it. So that would be 1 over I of x. And the derivative of the interior, that's just a power rule. You can multiply. So we have our exterior and interior, and the chain rule itself if we write it out is E prime of I of x times I prime of x. So the derivative of the exterior times the derivative of the interior. So putting it all back together, we have the derivative of the exterior, 1 over I of x, which is just the original, or x to the 8th plus 3, times the derivative of the interior, which is 32x to the 7th. So once we have those two parts, we can just put it all together, and we should. It's not simplified really as it's written in this first line. So that 32x to the 7th just hops on top. And we have our derivative.
And you can't reduce those leading coefficients because the exponents are not the same, correct?
No, we can't reduce them, but that's not why. So since we have a plus on the bottom here,
Oh, that's right. Okay.
we have a plus. If we're going to reduce, it has to be out of all of the terms. So 32 and 4 would reduce, and x to the 7th and x to the 8th could reduce, but that 3 is over here with none of those common factors. So that's preventing any reducing from happening. If that 3 were a 4, we could reduce because then there would be a 4 common in all of the terms.
If we understand like the concept of the E with the interior and the exterior, can we just jump straight to like the second step? Or do we have to include all of that on the test?
You don't. If you just include like this part, that's enough. This is enough work. If you like the
Thank you.
EI stuff, you can show this if you want to. So let's do that other chain rule problem from the previous from our chart.
Seven E is the exterior.
There's a little bit more to it.
So the X.
To the, I'm gonna write I of X.
Okay.
So 7e raised to our interior function is the exterior.
And the interior is 9X.
Exactly. So if there's stuff up there in the exponent that's not just x, that's going to be the interior function. So in this case, we have 9x, so that is our interior. So what is the derivative of the exterior?
Same.
Same thing, exactly. That's our exponent rule, or exponential rule. E to a power is just e to that power when we're doing the derivative. And the derivative of the interior is just 9. So same setup as before. So our chain rule says we have the derivative of the exterior, 7e to the I of x, which is just 9x, times the derivative of the interior.
60.
Yeah, so again, don't leave it like this. If you have two numbers that can multiply, we should. So whenever we're doing a derivative of e to a power, that exact same thing should always appear in our derivative. So we had e to the 9x. So that exact same thing is in our derivative. There's a little bit more here since it was a chain rule. So we had that 9 coming out. But that original e to the power should always be in the derivative after we take it. Those are the only two chain rule problems that I prepared, but I'm happy to do more if there are requests. You can think of one. That's good. The other question is, so we have 5 derivatives here. We have done 2 of them. And I would be happy to do more of them. Or if there are requests to go on to something else. We still have 45 minutes, so I don't feel rushed right now.
So I'm just reviewing my notes, and I made a note that says with the quotient rule to leave the bottom in the factored form. Is that still accurate?
Yes.
Cool. Thank you.
Yeah, in the quotient rule, we have that whole bottom just gets squared, and so yeah, just leave it squared. If you really felt like FOILing it out, it would be fine, but it's better to leave it factored. So Okay, I would like to do this number 5 because I think there are some issues with these radicals sometimes, especially now that we've done integrals. Sometimes people get confused between derivatives and integrals when we're going back and forth like this. So let's at least do that one.
And then after this one, can you show the answer for the last one? I forgot to look up when we were doing it.
Yes. The last one we did, you mean this chain rule one?
Yeah. Okay. That's good.
Okay, so our instructions here are to find x. The instructions on the test, by the way, use different notations for the derivative, like it might say find dy dx or y prime f prime. Okay, so we have 3 terms here. Each term is going to use a different rule. So before doing anything with the first 2 terms, let's rewrite this last term so that we can use the power rule on it.
Or x to the -1/2.
Exactly. So I want to do this in steps just to be clear about what's happening. So a square root is the same thing as a 1/2 power. 4 over x to the 1/2. And then we need to bring it up top, which means making it negative. That applies to derivatives and integrals. If something like that were to come up on an integral, we always want to get it to its format so that it's ready for the power rule. So x to a power is the power rule. So when it's down there in the denominator, it's not ready. So it needs to be up on top. And instead of having radical form, we need to have exponential form. So that is the first thing we should do if we see a radical or a square root or any kind of radical on an x, change it to an exponent and make sure the x is up top if it's just one term like that. Then we can do m. So we have 4 ln x. What would be the derivative?
Natural log. Or 1 over x. Or 4 over x.
Yes, exactly. So started writing. So it would be just 4 over x. It's fine. So right now we're doing d dx of 4 ln x. It's the derivative of that term. It would be fine to first think of it as 4 times the derivative of ln x, which would be 1 over x. But then to simplify, we would put the 4 on top. So it's fine to do it in 2 steps, but also fine to do it in 1 step.
Minus 7e to the x.
Exactly, minus 7e to the x. So that one doesn't change at all. And our last one. So here's where we need to be careful.
Power rule.
Power rule.
Is positive 2x to the -3 over 2.
Yes, exactly. So in this case, we had so that -4 is multiplying with the -1/2 that comes down from the exponent. And then x is being raised to the negative 1/2 minus 1, which is the same as 2/2. And that is where we get a positive 2, x to the negative 3/2. So you don't have to show those steps on the right, because I know that you can multiply -4 times -1/2, and I know you can subtract 1 from -1/2. However, it is often helpful to write those steps because it's easy to make mistakes on this kind of thing. It's easy to make like negative positive mistakes. It's also super easy to go the wrong way with these exponents. Subtracting 1/2, or excuse me, subtracting 1, sometimes people accidentally add 1. So it's good to just be extra careful there. So this is an acceptable answer. If you just leave the x to the negative 3/2 like that, that's fine. But also if you want to we can make that 2/x to the 3/2. And
I just have an unrelated question. So would that bottom exponent be the third? Okay, third square root of 2.
it actually isn't. I shouldn't have written that. It's a square root with an x cubed on the inside. I mistook that radical. So the 2 in the denominator of the exponent tells us what kind of radical it is. So it's a square root. And the 3 on top is just a regular exponent.
So if there was like a 4 in front of the radical sign in the original equation, would it be x to the 1/4? Right, okay, cool.
Yeah, so if it were something like this,
Right, yeah.
yeah, that's x to the 1/4.
Okay, cool. Thank you.
So do be careful on those kind of radical problems, because I think it's easy to make little mistakes. So. Okay, so I'm going to go back to our, oops, that's not it, our list of stuff. So we've talked about derivatives in general, particularly the chain rule, power rule. We've done both of those. Are there any requests to do either a product rule or a quotient rule, or both? You know, always chat if you want to. Okay, if we have extra time, we can always come back to those, but I feel like substitution is probably a thing that people would like to go over. Okay. So let's do an integration by substitution problem. So switching gears now, we were just doing derivatives, so now we have to reverse our brain and now think about integrals. So here is a substitution problem.
X cubed minus 5.
Exactly. So when we are doing a substitution, that u is generally the interior, what we think of the interior function when we're doing chain rules, that's our u for our substitution. So after we choose u, where you think x cubed minus 5 is the right u, at that point we should completely ignore the original function for a moment and just find du based on our u that we just found.
3x squared.
3x squared, exactly. 3x squared, and there's one little thing missing here.
Plus c? No,
dx.
yeah,
Exactly. So that is important because when we're matching what we have in our u and du with the original integral, we need to be able to match all parts. So that du always comes from the u. I saw on the last test some people finding u and then looking at the original integral and finding du from that, but that's not what we should do. Our du comes from the u, just the derivative of the u with the dx on the end. And then we can go back and look at our original integral to see if our u and du are going to be able to substitute for everything in here. So our u, we can start by looking at the u. So we have x cubed minus 5, and that is in here. So that is going to replace that interior part. That -4 power is just on that piece, so that's not going anywhere. The other thing that we have to replace, though, is the x dx. This is a faulty example. I'm going to put in right now a square. I'm sorry about that. That was an impossible, impossible problem that I had written. This should be x squared out in front. Okay, so now that this all looks good, so that would have been an indication that something went wrong, but I promise that won't happen on the test. So we have an x squared out in front and a dx. So those are the two things in our integral that we need to replace with stuff in terms of u. So there's a slight problem over here though, because our du is 3x squared dx. We want only x squared dx and not that 3. So that means we need to get rid of that 3 by dividing both sides by 3. Which really, I recommend writing it as 1/3 du equals x squared dx. So now this part is exactly what we have in our integral. So that's what we should be looking for. So once we replace our u part, everything else should be taken care of by the du. So that little step is something that was a little tricky on the last test. So two important parts to pay attention to here. The du comes from the u. Don't look at the original integral when you're taking that du. Then look back and see if there's anything extra or missing from the du and adjust it using regular algebra. So now with all of this stuff, we can replace everything from the original integral with stuff in terms of u. So that x cubed minus 5 to the -4th is now u to the -4th, since that whole inside got replaced with u. And the whole x squared dx is getting replaced with 1/3 du. So u replaced that interior part and 1/3 du replaced everything else. And I recommend moving that 1/3 out, and you can actually write it with with that 1/3 on the outside right off the bat. It's just nice to have it out of the way so that now our integral is just u to the -4.
And 1/3 u to the -5 over -5.
Not quite. So we have our 1/3 out here. When we're doing an integral with the power rule, the reverse power rule, are we adding 1 or subtracting 1?
Adding 1, -3
-3, exactly.
over -3.
Right. That is another place where it's super easy to make a mistake. So we have -4 as our original exponent. When we're integrating, we raise the exponent by 1, which means adding 1 and dividing by that new exponent. And we have to remember our plus c. So this can now simplify. And I'm just going to simplify it without changing the u for a second. So that 3 and -3 can multiply on the bottom. So the integral has been taken. The integral is done. We raise the power by 1 and divided by the new power. We simplified those denominators. What's the last thing that should happen here?
Substitute u back in.
Yes, exactly. So that u was originally x cubed minus 5. So now that has that power of -3 and we have -9 on the bottom. C kind of looks like an E. Let me fix that. This is another one where there's like a few different formats that you can use. Honestly, it's a little bit weird that that negative is in the denominator, so I wouldn't mark it wrong, but it's usually better to bring a negative up top instead of have it in the denominator. So that would be fine. You can also make that exponent negative by bringing that whole thing down. So there will be a substitution problem, and that one actually says in the instructions, use substitution to find this indefinite integral. We also have one definite integral by hand, which does not use substitution. Which I think we should do. Are there any more any questions about substitution or requests to do another example?
Can we do one of the ones like on the practice test, like 10 and 11?
Let me see. Or those are the partial derivatives, right? Yes. Let's do one definite integral just while we're in integral mode, and then let's do partial derivatives. We will have time. Okay. On the test, it seemed like most people had an understanding on test 4. I mean, if you had an understanding of how to do this, but there were just like little things that were going wrong along the way. So if we are finding the definite integral of this, so definite integral is when we have these limits of integration, we're actually starting and ending at a place, which means our answer should actually be a value and not a new function. So we use those same integration rules as we did before. So just looking at the 2x minus 4 without thinking about the 6 or the 1 just yet, what would be, what's the antiderivative of that?
2.
That would be the derivative.
Oh, the antiderivative, sorry.
The
X squared.
or x.
X squared minus 4.
Yeah, what she said.
Yes. I think there is a little unison going on there. So x squared comes from taking that x from here, raising the power by 1. So it has a 1 for a power right now. It goes up 1 to the 2. And we divide by the new power, which turns it into just x squared. So 2x becomes x squared. Oops, excuse me, 2x squared over 2. And then the 4 just gets a little x added onto it. And we can always check if you're ever unsure about your integral by just taking the derivative of what you got. So x squared minus 4x would be 2x minus 4 if we do the derivative. So we can always do the derivative to check our integration. But we are not done because we're evaluating now from 1 to 6. So integration rules get us to our antiderivative, but now we need to do our evaluation. And I think this is where a lot of the little mistakes happen. So first thing to keep in mind is that the top number always goes first when we are plugging in. So that 6 is going to be what we plug in first. And that's going to subtract. The same thing with the 1 plugged in. And here's another important point. The whole thing with the 1 being plugged in is being subtracted. So we need parentheses around all of that. And from here is just a matter of evaluating. So we have 36 minus 24 minus 1 minus 4 is negative 3. So that's 12 plus 3 is 15. So just do be careful on this kind of problem. It's the little evaluation things that tend to cause some issues. Okay, so let's look at some partial derivatives. Are there any questions about this one before we move? Okay. So partial derivatives. So there's a couple ways to tell that this is a partial derivative and not a regular derivative. One way is that we have these weird looking D's. That means it's partial. But the other way to tell it is that we have more than one variable in here. So since we have x's and y's, if we have a multivariable function, there's no just regular derivative, it's all partial derivatives. So we're gonna find dz dx.
That means you find it in terms of x, right?
Exactly, yes. So x is our variable here, even though x and y are both technically variables. When we're doing a partial derivative, we have to specify this is the variable now, and anything else is just a constant. So we only care about terms that have x's in them. So x cubed, y squared has an x in it, and for x squared, y squared also has an x. That minus 2y cubed does not have an x in it, which means that this whole thing is just a constant. Which means it's going to completely go away when we do the derivative. So we only care about terms with x's. So this first term, we have x cubed y squared. What would be the partial derivative with respect to x of that term?
Three x squared, y squared.
Exactly. So remember, the y part doesn't do anything here. The y is staying exactly as it was. It's still an x squared, but we do the derivative of the x cubed just like normal. So how about that next term? Or x squared, y squared.
8x y squared.
Exactly. 8x y squared. So again, the y part is just a thing that's multiplying. It's just hanging out, just like the 4. But the 4 gets to multiply with the 2 that comes down, and the exponent of the x drops. So nothing happens with those y's. And that minus 2y cubed doesn't do anything because it's just a constant when we're focusing on x. And that is our whole answer. On this one, I didn't specify on the test that you don't need to show work, but you really don't here. There's nothing to show. This is just the power rule, so we really don't have any work. There's thinking. And of course, if you like to make notes, you're more than welcome to show more than this, but really it's just that one step. So this is a first order partial derivative because we're just doing the derivative one time. We will also have a second order partial derivative on the test. And I'll tell you right now, the second order partial derivative on the test uses this notation with the f and the little x and y. It does not use the dz dx. The first order partial derivative on the test does use this notation with the weird dz and dx. But it's confusing for second orders, and our application problems use this order most. So I am putting that on the test for that one. Okay, so we have this function, this 2-variable function, where we want to find the partial derivative with respect to x and then y. So always remember in this notation, we're doing x first. The one that's closest to the f comes first. So we will find fx. And I left off the xy here. it doesn't. The important part is doing the derivative. It doesn't really matter if we write just f with a little x or f with a little x, xy. So here we're going to again do the partial derivative with respect to x. What will we get there?
Nine x squared plus 6x y or 6x times y squared minus 4.
Minus 4.
Y.
Yes. Right. So we're starting with that original function. This 3x cubed got its derivative taken, 9x squared. This 2y squared is nothing when we are focusing on x. There's no x in there, so it just goes away. It's a constant. The 3x squared y squared gets its derivative taken, and that y squared doesn't change. And 4xy is just 4y. So doing the derivative with respect to x that time. So this next step, I think, is where some confusion happens, which is when we're now doing what we are trying to find in the end, the derivative of x and then y, we're starting from this step that we just found. So we just did this step, the derivative with respect to x, and next is the derivative with respect to y, starting from the answer that we just got. So the original function is unnecessary now. We're starting with this first statement, or the second statement. So now we have 9x squared plus 6xy squared minus 4y. So when we do the derivative of that with respect to y, what will we get?
2y minus 1.
Was it 6x 2y minus 4?
Yes. And we can simplify a little bit there still. But yeah, so the 9x squared is gone. That goes away because there's no y in it. The next term, 6xy squared. So we can think of it as just 6x first, so those two things aren't changing. The y squared gets its derivative taken, so that 2 would come down, and the power of the y goes down by 1. And the 4 would be the only thing left for the last term. And that does need to simplify into 12xy minus 4. And you can go straight to the 12 also, but either way. So this kind of problem is necessarily a two-step problem. There's no way to do this all in one step. Maybe with lots of practice, you could do this in your head in one step, but even if you're doing it in your head, you would still be going through 2 steps to do it. So don't do it in your head. You need to show these 2 steps, but it is necessary to go through the partial derivative with respect to x first, and then use that to go down to the y. Any questions or concerns about that second order partial derivative? So this is the kind of thing, these will come up, well, most of this will also come up on your take-home test, but they just be super careful to pay attention to what variables we are doing the derivative with respect to and the order that they're in. So we have talked about those things. Those things. So the only, oh, we did that too. So the only thing that we have not reviewed is the problems using the product rule or quotient rule. So I would be happy to finish off with that unless there are any other specific things that you wanted to clarify about the other stuff. Okay. I'm gonna just FYI, I'm gonna keep these sorry, my brain. I'm going to keep all of this in sort of the order that we're doing things, or the the order based on like chapter 2 through chapter 5. So I'm putting this quotient rule problem in with the other derivative stuff. So if you're looking at the class notes later, it's in order by category, not by order that we did it in class. Okay, so just an example, sometimes it might be y prime, sometimes it might be dy dx. This is a normal derivative, so we use the normal d's. And the quotient rule is bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So we should always identify the top and the bottom, which is just the numerator and the denominator. Then we need the derivative of the top and the derivative of the bottom. So the top here is just a power rule, so we have 10x. What's the derivative of the bottom?
Three e minus 2.
3e to the x minus 2. So that 3e to the x doesn't change. It's its own derivative, and then the minus 2 is left from the x. All right, so now we just have to put all of this together. I'm afraid I might not have left room. So we have the derivative of the bottom times the top minus the, nope, that is not right. The bottom times the derivative of the top minus the top times the derivative of the bottom. There we go. All over the bottom square. So this is great if you get here. However, I do want you to simplify at the top because there might be like terms that can be added. So in general, the top shouldn't be left with sort of two separate complex terms on top there. So we do need to multiply out. So we'll have 30x e to the x minus 20x squared. Be super careful here. A big cause of issue on these is that minus sign on top not getting distributed to where it needs to. So in this case, we have minus 5x squared that's going to distribute. So we'll have negative 15x squared e to the x plus 10x squared. That. And so here's where we need to be careful to combine like terms. We have 2x squareds on top, so that can simplify. And if your terms on top are in a different order, it's okay as long as each term is correct. So that's just one thing I wanted to note here is that we do need to simplify the top. So we don't have time to do a product rule problem, but we've covered just about everything that's on the test. So test is on Thursday, normal time, normal procedure, and everything. Next Tuesday, we will do review for the second part of the test, so please bring questions to ask about that. And I will see you on Thursday.
Thank you, Madeline. Have a great day.
You're welcome. Thank you.
Bye-bye.